our universe computes, and my question has been, is geometry equal to computer science? So let's see what the heck do I mean by that? So, I claim that mathematics is a larger set than computation. So mathematics contains all the things that we even can't see that are possibly uncomputable. And computation, in a sense, is always coming from somewhere. It's almost as if this is what it means to have a perspective. And computation, and as we learn from the sort of Maxwell's demons, computation gives off heat. You don't do it for free. So it is intrinsically physical. What is the actual natural geometric shape that our universe takes? So here's the definition. The critical density of the universe refers to the average total mass energy density of the universe required to make the geometry of space-time flat. So in cosmological models, the geometry, also known as curvature, of the observable universe depends on the average total density of matter and energy within it. If the average density is less than the critical density, space-time would have negative curvature, like a saddle. If it exceeds the critical density, the universe would have positive curvature, like a sphere. Who's heard of these claims that we're living in a simulation and it feels a little bit like the Matrix, like, ooh, everybody is special and it's coming, we're in this strange video game. Yeah. So that intuition comes from the Church Turing thesis, which I'll explain in a bit. But I think that that's pretty sketch. It's pretty sketchy. So there's also this question about whether, it's not really a question, most physicists don't ask this question, but there's this notion when you come from math, coming from those sorts of geometric intuitions, you can say, well, is the universe, the cosmology, really a finite container or is it an infinite container? And, well, this is the kind of complete list of people who have argued for this notion of finite and extent. So some cosmologists suggest that the universe can have an overall positive curvature, like the surface of a sphere. And if the universe curves back on itself like a sphere, it has finite volume. Okay. Multiverse theories. Models have been proposed in which our observable universe exists as one finite bubble among countless others in a larger multiverse. So now, going from the very big to big simulation that the universe is doing to compute us, right? And the universe computed us, right? We don't know how, but we got here somehow. Quantum computers are local. They're these local simulations. Instead of this big picture, they're these just local simulations of what's happening in these very precise dynamics in physical reality. They all can be built to the level of 100 million or more qubits. So we have to be careful, we have to be good engineers, we have to make sure that we're taking into account all of the heat loads that come from every stage of the stack, which often are even the best professors that you'll have don't do that. I just categorize this as first generation, second, third, and fourth, just in the sense of what's really been more widely looked at. So we have these ion traps that we know they're very slow. They're the slowest in terms of gate speed. They have a large footprint. Here we have linear optics, diamond, and other spin-based systems sitting at megahertz in physical speed. And as we talked about, when you go to logical speed, it's dropped. The gates are actually slower. You have to account for that. what's called tensor networks, quantum tensor networks, because it's a black hole, as it were, right, on very small scales, and trying to understand if, just understand the connection. So I asked this question in 2017. Folks at KIP in Santa Barbara, it's like, well, okay, if you have this map, right, it's not just about the map, but is there any way that we can think about the tensor networks as software, right, in some kind of precise mathematical way that would allow us to simulate many body systems and maybe even understand something about gravity.
I just would like to say thank you for this time and so we all, I think, very appreciate them.
Thank you.
And this is a small gift from KAIST, okay, Graduate School of Quantum Science and Technology. You know, that's our mascot.
Woo!